This talk is going to deal with types of chemical reactions. And as I'm talking about reactions, I'm going to be using symbols. As you can see, I'm going to be using symbols such as A, B, and C to represent the positive portion of a molecule. And I'll be using X, Y, and Z at the end of the alphabet to represent the negative, the back end of every neutral molecule. We want to talk about types of reactions, and the first type of reaction is a composition reaction, sometimes referred to as a synthesis. And as you can see in this example, we're going to have a positive component come together with a negative component to make a neutral molecule. Let's look at some examples. Sodium. Sodium in the first family, we think of it as having a charge of +1. And chloride -1. So the two ions would come together to form a neutral sodium chloride. Well, there's a problem with this reaction. First, chlorine comes in diatomic form. So we're going to have to put a 2 here. This gives us good formulas. In every reaction, the first thing you do is write good formulas. But now that we've written good formulas, we have to balance. So I didn't leave a lot of room, but we're going to put a 2 here so that we'll have 2 chlorines. And then because of also having 2 sodiums, we would have to put a 2 here. So this will give us a correctly balanced chemical equation for the synthesis of sodium chloride from the elements. The second reaction I have here is hydrogen. But you know that's not right because it has to be diatomic. And oxygen, also diatomic. And that's going to produce water. Well, the oxygens are not balanced. So the first thing we'll do is start by putting a 2 in front of the water molecule so that we have 2 oxygens on both sides. This leaves the hydrogens imbalanced, and so we would have to put a 2 on the reactant side so that our coefficients would lead us to see that 2 molecules of hydrogen would combine with 1 molecule of oxygen to produce 2 molecules of water. We'll come back to these a little bit later, but they fit the format of combining 2 particles to make 1 larger one. You might say a onesie plus a onesie yields a twosie. Let's look at decomposition reactions, a second type of reaction. And decomposition reactions are of the format a large particle with a positive and a negative component will break up into smaller particles. And so there are probably 4 good examples of decomposition reactions, but let's focus on 2 that will become more important in later parts of the curriculum. All right, let's look at a base. A base, as we already know, is going to have hydroxide as part of the formula. That's our definition at this point. So, when calcium hydroxide decomposes, what would it decompose into? Well, one of the products will be water. H2O. So just look at the formula. If you take out 2 H's, they're all gone. And one of the oxygens, that leaves us with calcium oxide. Calcium oxide. Now, calcium oxide is a metal oxide. So when bases decompose into metal oxides and water. All right? This reaction could be written in the reverse because if we were to take these 2 simple units, an A plus a B, we could put them back together, and in the reverse direction, we would be making calcium hydroxide. Let's remember that a reaction in the forward, that is a decomposition, would be considered a composition if it's going in the reverse. if the calcium oxide is dissolved in water, it's going to form calcium hydroxide, a base. Well, there's other terms that we want to bring up here, because calcium hydroxide is indeed a base. And this is water. So, how would we describe this component of our equation? Well, it's a base without the water. And there's a term for that. It is called a basic anhydride. You know, when you're thirsty, you're dehydrated. And when you drink a lot of water, you hydrate well. And so anhydride, or anhydrous, means without water. In the lab, you've seen the reverse of this, because in the lab you took magnesium oxide, which was the white powder that you created in your crucible, and you added some water to it. And what you did then was the reverse of the first reaction, with a different substance though. And here we created magnesium hydroxide. Or, if you had created magnesium hydroxide, you could have heated it up, driven off the water, and been left with magnesium oxide. Okay, so this is one reaction. Now, let's take a look at the second decomposition reaction, which is the decomposition of an acid. And if we have an acid decomposing, let's use a very common example that comes up often in the course, H2CO3. That is carbonic acid. And when carbonic acid decomposes, what you're going to form is water. Now, what is the other component? Well, let's take H2 and an oxygen out of this formula, and what we're left with is CO2. In this case, the product that we're forming here is a nonmetal. A nonmetal oxide. You're very familiar with this reaction, because every time you open a soda and you release the pressure, you hear psh, and the bubbles of carbon dioxide gas rise to the top. So all the carbonation goes away, and your Coke or soda product is going to start to taste flat over a period of time. We can look at these products too, the reactants and products, and if this is an acid, and we're removing the water, then what would be another name for this product, the carbon dioxide? It would be an acid anhydride. And the acid anhydride is just the acid without its water. Now, all this becomes very important when we start to look at a periodic table. Because if we are looking at metal oxides, and let's just take this out a little bit, if we're looking at metal oxides, we're looking at elements that are on the left-hand side of the staircase. These are our metals, and this is where we find our good bases. Sodium hydroxide, lithium hydroxide, potassium hydroxide are good bases. And as we move towards the right, those bases are not as strong. Where do we find our acids? Think about it. Don't the acids come from hydrochloric acid, hydrosulfuric acid, sulfuric acid, nitric acid, phosphoric acid? So on the right-hand side of the periodic table is where we find our acids. On the left-hand side of the table is where we find our bases. This is a periodic trend. It's a pattern that we'll be studying and looking at later in the course. All right, so let's move on, and let's now talk about the third type of reaction. And the third type of reaction is a single replacement reaction. You probably noticed that out in the left-hand margin, I've used some abbreviations for these types of reactions. Sometimes in my notes, I'll just refer to an SR, a single replacement reaction. But let's look at what is involved in a single replacement or a single displacement reaction. Here, we're going to have a onesie combining with a twosie. And by using A, I'm saying that I associate this with a positive substance. We're going to exchange the positives. The A and the B will exchange, and the products that I will form will be B plus AX. The order does not matter. You could write AX plus B. And a good example of this is the replacement of, I should say, a metal by a more active metal. And for this, you need to understand something about the activity of metals. You know, when we're looking at a periodic table, the most active metals are found to the far left. So the most active metals are going to be, let me zoom out again. The most active metals are going to be in the first family: sodium, lithium, potassium, rubidium, cesium. And the second family, where we have our +2 ions, and even some of the third major family, where we find aluminum. It's going to be a lot to remember which one is more reactive. But the general trend that we'll talk about is that as you move to the left and down, metals become more active. To the left and down. So on this table then, francium is considered to be the most active metal. So sodium is more reactive than lithium, and sodium is more reactive than magnesium because of the positioning on the periodic table. Sorry about that one. Sodium more reactive than lithium because it's farther down. Sodium more reactive than magnesium because it's farther to the left. To the left and down is where you find your more active metals. But look at what we see here shown in yellow. This upside down T. If you look at the elements that are found there, these 5 elements are often referred to as precious metals because we use these to make our jewelry. These are the least reactive metals. And these, you can put this T on your periodic table. You need to be familiar with them because usually when you see these elements by themselves, they are not going to replace the element, the metal in the compound because they have so little activity, chemical activity associated with them in comparison to the one that's in the compound. So make this mark on your periodic table. Copper, silver, gold, platinum, all things that we consider making jewelry out of. And we know how jewelry is precious. Our religious artifacts, our wedding bands, things that we want to endure forever, we're not going to make out of some metal that's going to rust and fall apart once it gets wet. So looking at this reaction then, let's take the example of iron plus copper chloride. Well, I see the copper and I know that it's that metal that we use for jewelry, copper bracelets, and so it is not very reactive. Okay? This metal, the one by itself, is more reactive. It's not a precious metal. So these two metals are going to exchange, and the products of this reaction is going to be copper and iron chloride. So this gives us a good idea of the first 3 types of reactions that we need to be familiar with.